All right, welcome everyone. Today we're going to have a colloquia speaker today. Dr. Anthony Yee from Lockheed Martin out in Palo Alto is going to be giving a talk. Anthony Yee joined Lockheed Martin's Advanced Technology Center, ATC, in 2019 after receiving his PhD in optics from the University of Rochester at the Institute of Optics. His doctoral work focused on infrared gradient index optics, metrology, optical design, and athermalization. He's currently a senior optical engineer at the ATC and Optical Payload Center of Excellence, working on optical design of telescopes for interferometric imaging. I've known Anthony since he started his PhD work. He was a really good student at the U of R, took my class, all that. And Lockheed is looking for interns and employees and all of that. So if you're interested in the type of work that he's going to talk about today, you may want to talk to him after the colloquia, and there's a couple other folks here from Lockheed that you can talk to as well. So with that, take it away.
Thanks, John. So I'm Anthony. Thanks for the introduction. So I'll be talking to you about SPIDER, which is a chip scale interferometric imaging sensor. So this is part of some work that's going on at the ATC, but I'm also part of this Optical Payload Center of Excellence. So we make payloads for space, and this is kind of some next-gen, future generation technology that we're working on to try to shrink it down. So I'll kind of give a long introduction into this next generation topic. So as John said, went to the other school, Rochester. And so my work's in gradient index optics, which is not really related to this topic, but you kind of apply everything you know to it. And so I'm working on interferometric imaging, laser communications, and a lot of optical design for various projects. So a little bit about Lockheed Martin. We're over 100 years old. We have almost 100,000 employees, and 60,000 of them are scientists, engineers, and IT professionals. We have almost 600 facilities around the U.S., so around every corner there's an office there. And you might not have known this, but we hire approximately 5% of all engineers trained across the U.S., which comes out to about 4,000 people annually. So we're a big company. We have four main business areas. We kind of joke they kind of act like small individual companies. So if we tease that if you were to change divisions, it would be like applying for a new job. We kind of don't interact with each other very much. They're pretty separate. So people will be like, oh, do you know this person at this company? And you're like, yeah, they're part of Missiles and Fire Control. So I work at Space Systems in the bottom right, and kind of our big areas that you might hear about are aeronautics and space systems, since the aeronautics group makes the big fighter jets, the F-35, and Space Systems makes all the scientific instruments that you hear about. So a little bit more about space, focusing on space systems. Something that people might have taken for granted in this day and age is how reliant we are on space systems. Everything from your GPS to when you do bank transactions, your cell phones and your cable TV. These are all reliant on space systems, and space systems have infiltrated your everyday lives and will play a bigger part in your future as we keep going on. So Lockheed Martin has been actively involved in the design and development of space systems since the dawn of the space age. Our fundamental business is in building satellites, which have to operate for years in harsh environments and have no options for maintenance, as we can't just kind of bring your car into the shop and get repaired. We bring them into space, and you can't really do anything to them after that. So they have to be maximized for energy efficiency, as a lot of them are powered with solar panels, and we want them to be optimized for size and mass, as they both drive the cost. And anything you launch costs a lot of money, so the smaller it is, the better. But oftentimes with optical systems, the bigger is better. You always want more space. So those are kind of the constraints that we typically face when trying to physically, design and launch.
All right, so that's unmuted.
What? Okay. It's good to be. We don't do too much stuff with audio, so. Where was I? So yeah, as you can see on all the different space stuff we do, we work in civil space, military space, commercial space, all areas of space, and underpinning all of our projects is a core set of people, techniques, and facilities for advanced technology and architectures, and so that's where the ATC comes in, or the Advanced Technology Center. So this is where I got hired into. We work closely with them in the Optical Payload Center of Excellence. And we're an R&D laboratory of approximately 500 scientists. It's kind of a small group within Lockheed, but most people wouldn't consider 500 scientists small. It's kind of big for most people. But the goal of the ATC is to come up with new architectures and disrupt technologies that will give us some sort of advantage in making lighter weight payloads or give us lower power on our systems. And our goal isn't really fundamental research or fundamental science, but rather hardcore engineering. So how to do things better, cheaper, and faster. So we do contracted independent R&D work. We have a lot of payloads and payload technology. We have a big group that does space and earth sciences. So that's kind of where maybe we do most of our fundamental research. So they do a lot of solar probes. And then we do a lot of classified programs. And because a lot of us have advanced degrees, we have pretty strong ties to the U of A and other R&D and government institutions that we work on with a daily basis. So we're doing work that's looking forward and focusing on discriminators for the next generation of programs and seeking out capabilities to create the new technologies to make a difference. So these are kind of the different topic areas that the ATC specializes in. With 500 scientists, you can imagine that we have a diverse range of expertise. Kind of these are our core competencies in electro-optics, phenomenology, space sciences, advanced materials. And there's kind of a wide range of research that goes on at the ATC and has been around for a long time. So Lockheed Martin Space has a long record of payload history. We've made over 180 space instruments over the last 6 decades, ranging from X-ray all the way to long-wave IR. You can kind of see on the timeline from 1960 to present. We've done all these different payloads that these are kind of the ones we can show. And the Optical Payload Center of Excellence has kind of grown out of this ATC and this history of payload expertise. It's kind of the current organization that focuses specifically on the design and development of optical payloads and advancing that technology. So some of the programs you might have heard of, we kind of pull them out because sometimes they're in the news. IRIS is a satellite launched in 2013 to study solar storms. NIRCam, you've probably heard of. We collaborated with you at the U of A for this. It's the primary scientific instrument for the James Webb Space Telescope. And then space domain awareness is something I'll be kind of talking about today that you might not have heard of too much. But it's a capability that we're developing to track and characterize space objects, being satellites or debris. We spend, these are kind of the areas that we spend a lot of time caring about, time and energy. Directed energy is kind of a big topic for us these days. So high-power laser programs working in the field. So not just a high-power laser in the lab, but it needs to work in a turbulent environment where things don't behave the way you think. So there are a lot of problems to solve when you kind of don't know how the media they're traveling through is changing. So this requires really good optical and optomechanical control and thermal control, as you can imagine, to deliver a high-power laser over some distance. We work on laser radar, and then advanced materials and manufacturing. We have these things called nanocopper and lead-free electric assembly. It's kind of our bread and butter at the ATC. I don't know a ton about it. I'm not in the materials group. But it's maybe not something you think we would spend a lot of time and money in, but when you're trying to make everything better or last longer in these harsh environments, materials become key to everything. And so materials kind of underpin a lot of what we do and create a big competitive advantage to what we do. So we're optics people. So here are some of the tough problems I kind of care about, or we care about in space and as optics people. In the context of satellites, we're always trying to reduce the size, weight, and power. You always hear SWAP. Mass is always a big thing when you're going into space. Is you want to put as much capability onto your satellite as you can, and making it bigger always makes it cost more. Whenever you put up there and launch, it has to pass, the thermal and vibe testing, and that's always a problem. The next question is, how do you make an imaging system smaller without reducing resolution? And we'll be talking a bit about that today. That's kind of what SPIDER focuses on. But not even launching things into space, but increasing the ability to resolve things from further away, whether it's from ground or, to space or space to ground. As you definitely know here, there's a limit to the aperture size that you can build. It's kind of hard to build really big primary mirrors. Whether or not it's going to space or not, where launch can be expensive and things like that. But there's also just a kind of a practical limitation to how big you can make something. So aperture size is always, what can we make 100-meter aperture optics? One of the other tough problems that we think about a lot is enabling the full potential for lasers. So lasers are something that work well in the lab. I kind of mentioned it in the directed energy, but we haven't really seen the full potential of lasers, especially kind of outside of the lab and more in environmental turbulence and things like that. So over the next 30 years, that's something we think will become a bigger area in laser communications, active imaging, and more. And so beam control and is becoming more important with directed energy and laser comms. So and with lasers, we always want more power, more efficiency. That's a lot of what we care about. And so the areas we are addressing for some hard optical problems is space debris management using lasers for space debris management, sparse aperture imaging for space domain awareness, and making basically imaging systems with a smaller hardware footprint using photonic integrated circuits. I don't know if you've seen some pictures like this on the right, but if you've ever seen a talk on space debris, it's not pretty. So space is getting really crowded. The chance of collision is increasing, and what's shown here is a picture of the Earth surrounded by everything that we have cataloged orbiting around it. And this only shows debris that's 10 centimeters or larger. So anything smaller than that's not shown here. So you can just imagine there's tons more things floating around here that you just kind of want to wipe away and get out of the way. And so there have been incidents of satellites colliding with each other or debris, and this only makes the problem worse as they collide and they break into smaller pieces. And the cost of trying to maneuver your satellite is high. You're basically decreasing the lifetime of your satellite every time you're using your fuel to move it out of the way, and it's a problem that's becoming more of a problem. The need to know where everything is and characterize and mitigate debris has increased. In this swarm of objects that is shown, only about 4,000 of them are objects that are operational payloads. So not just debris from crashes up there, but every time you launch a satellite, you leave the shell around the satellite, the stages, and rocket motors. So there's a lot of junk floating around there that you might not even be able to control if you're about to run into each other, or not everything's always moving. And so it's been a big problem. As a spacecraft provider like Lockheed Martin, we're interested in protecting our operational satellites. But for everyone else, is this a problem? Well, the answer is yes. And it's going to be more of a problem as we care more about or become more reliant on space systems. There's a potential for debris-on-debris collisions. sure, if we know that something's going to collide with us, we can move out of the way. But we already mentioned that, that shortens the lifetime of our payload. But what happens if you no longer have control of your payload? So say you can't move it anymore, but you can still communicate with it. So you still might care about not trying to crash into something. This plot on the bottom right shows what's called as the Kessler syndrome, which is the potential for debris-on-debris collisions to continue to the extent that it's a runaway problem, and there's nothing we can do about it. And so this is challenging all the orbital layers that we're interested in, not just near-Earth orbit or low Earth orbit. It's all of them. And so what are we doing about this? So project we worked on in the past was called NASA's Light Force concept. It's not as exciting as shooting a harpoon and pulling back all the space garbage, nothing that extreme. But if you were to think about the problem, how would you get these huge debris down from space? It's completely uncontrolled. You have no propellers on it or any fuel. And it's not really a problem that some people have solved yet. So the light force concept is, instead of shooting out of the sky, which isn't that practical, the concept is to use a giant laser on the ground and apply just a little bit of radiation pressure or photon pressure on the debris of the object. So if you could hit the object and impart just enough momentum that over the course of several days, if you keep hitting it, you can nudge it a few millimeters or centimeters. You could do it enough times over some period that you could change the trajectory by hundreds of meters by changing its orbit. And this could be a way to try to avoid a collision where you wouldn't have any other options, whether you can't move your payload, but you want to move the debris that's potentially going to collide into your payload. And right now that wouldn't work with very large objects, but maybe smaller pieces of debris that could come and damage your system. So it's a start, the problem will only get worse. That's something we have to continue to think about. So what are some of the technical challenges being addressed? In order for this to work really, really well, you need good conjunction analysis and conjunction prediction. There was the Iridium Cosmos satellites collision where one was a working satellite and the other wasn't. And it was a question of, how close are they going to get? Are they going to collide to each other? And based off of the information they said it would know, it'd be something like, they'd be like half a kilometer away and they wouldn't crash. But obviously they collided. And you would think we would know better than, half a kilometer that whether two things are going to hit each other in space. But it's not that easy. We have these non-conservative forces that, such as solar winds and radiation, that kind of are not easy to predict as they're orbiting, and it's not really a solved problem of figuring out the orbits. So the question is, if they had better analysis of where things were going to be or things exactly are, maybe they would have been able to figure out that they were going to hit instead of not. So with different results, with better conjunction analysis, with improved orbit propagation and tracking, they could have done a better analysis. But limitations using radar with how good we know where something is kind of where we're at, but LiDAR or laser radar is getting better, so we can kind of with better resolution, kind of know where objects are. So, the better we can track the orbits, the more data we can have and put into our analysis. That would still give us maybe a few days of prediction of where things are going to be, but if you try to do a week-out analysis, still with these non-conservative forces, it would be hard to predict. And so to keep track and good understanding of where all the space debris and satellites are up in space, we'll do better to keep track if things are going to collide or not. And to do the radiative pressure, the light force, we would need really good beam control. So, in order to send a big high-power beam up into space, you would need really good beam control in order to go through that turbulent environment and to get as much power as possible. So things like adaptive optics and high-precision beam control are really important. So we have this facility in Santa Cruz. It's about 20 miles from San Jose, south of San Francisco. It's about an hour drive, I guess, from our facility. We have 3,600 acres of land that we do a lot of field testing with. But we also have this facility that we call SPOT that works on space domain awareness, and Michael Hart here provided the adaptive optics systems for this. So the spot down here, sorry, is 3 1-meter telescopes on mobile domes that we're working on to do high-resolution imaging of geo systems. We also have satellite tracking and illumination, LiDAR trailer stilt. And so, yeah, we're developing kind of the next generations of space domain awareness, passive and active imaging, interferometric imaging up in our Santa Cruz facility. We also do a lot of other cool work up there since we have all this land, but can't say too much about that. So in Santa Cruz, we kind of operate mostly from March through October. The seeing conditions, our R0 is about 5 to 10 centimeters. In addition to doing traditional imaging, we developed technologies where you can do fingerprinting of satellites, other signatures without having to do active imaging. And I wanted to show some of the data that not just visible sensors, but hyperspectral and hypertemporal sensors can show. So don't ask me too much about what the data means. It's just kind of a cool thing that I saw from someone else. I'm not a huge expert on this, but this shows the intensity versus wavelength. You might not be able to see it on this. The intensity versus wavelength of different satellites. So just by looking at the spectral information that the satellites are reflecting, they're massively different depending on who made the bus or what kind of instruments they have on it. And from that, you can identify satellites by their type, potential, and the potential to fingerprint and identify and characterize the state and unusual behaviors. And if you, again, look at the hypertemporal imaging, when light is reflected from to the ground, the object vibrates in a certain way based off of the mechanical structure. And this unique signature, by looking at the hypertemporal, can be used to figure out what's there, but also give any indication of the state changes or the health of the satellite. So you can maybe not resolve the actual image of the satellite, but you can get other information and still tell what's going on with the satellite. So back to the more traditional imaging for space domain awareness. It's a hot topic of ours, especially for geostationary objects. Just a quick refresh, geostationary, geo is 35,000 kilometers or about 22,000 miles above Earth. We have trillions of dollars of assets in geo. And we don't really have many options for problem identification as we can't really see them very well. To the extent that in April 2020, there was a communication satellite, Galaxy 15, that we could still get information, but we couldn't control. Not we, but them. It was a zombie satellite. And they didn't have much information as to what was going on. Was it, what went wrong? Did it start spinning? Something like that. And it's kind of amazing that how little information we have on these satellites once we launch them up there. Whereas in LEO, low Earth orbit, we can image them using a standard telescope on the ground. You can get a pretty good image of some information. But geo is so far away that even if we were to use our largest telescopes, it would look kind of like a smudge. You really wouldn't be able to tell what's going on. But as it is, there's not much else for imaging geo. So being able to monitor these trillions of dollars of assets in geo is really important to the customer. So this is kind of a nice comparison. So if we wanted a Google Earth type image on a geo satellite, we would need a greater than 70-meter aperture on the ground. And so the next generation billion-dollar telescopes is 30 meters, like the 30-meter telescope. So that wouldn't be give us the full resolution that we'd want to image a geo telescope. So what can we do? And so that's kind of where we look at stellar interferometry. So It's something that kind of comes into popularity and in and out of popularity every now and then. So instead of having to make a really large aperture telescope to get the resolution you need, what if instead you split up your telescope? Instead of having one, you took two smaller telescopes and put them in a particular distance apart. If you're able to combine the light in the right way, you could synthesize an aperture that has the resolution of the distance between them. No longer the actual aperture size, but rather the distance between them becomes the thing that drives the resolution of the telescope. So this is something that Michelson did a while ago in 1919, and has still been in and out of popularity and comes back here and there. One way we see being able to achieve this in our science is for our science objective of geosatellite imaging. One thing, though, is that the beam combination hardware is very complex, but it's an option. So how does this work? So for example, so say we have light from a star, comes down through the turbulent environment, and gets different wavefront errors on each telescope due to the different media that is passing through. And light from the star will hit one of the telescopes first due to the geometry, so you can kind of see that there's wavefront coming in at an angle, hits one telescope before the other. So if it's on one side, it'll physically be received on one telescope first, and in order to interfere the two beams to make a white light interference fringe, you need to make sure that you delay the light from the telescope that you received first, the right amount. So you can see that we have a little bit of a delay line to match the difference in optical path of the two telescopes. And if you do that just right, then you can get an interference between your light, and you should have a white light interference fringe between them in theory. While in practice, it's a little bit harder. So here's just a little animation that kind of shows what's happening. So say we're trying to look at this geosatellite. We're no longer looking at a star in this case, but we're on the ground, and we have two telescopes that we want to try to image the geosatellite. So basically what we're doing in stellar interferometry is you're no longer forming an image in the same way. You're effectively sampling the Fourier transform of the intensity distribution. So as light is either emitted or reflected from the object, it diffracts and interferes. The higher spatial frequencies are diffracted at wider angles. So look, this cartoon on the left here, the top one shows that if you have a large aperture like this big gap over here, you get a narrow diffraction angle, whereas if you have a small feature over here, then the light diffracts at much wider or larger angles. And the actual object that you have will have this, so this kind of shows kind of a more real object. We'll have a crazier interference pattern or diffraction pattern. And so this is kind of a side view, and this middle plot shows 2 points and the diffracted pattern kind of in a 2D picture. So you can see that two little dots of different sizes gives a much crazier pattern. And then for even more complex than a couple dots, you have a satellite. So this is the satellite, and this kind of shows the Fourier or UV plane spatial frequencies for such an object. Sorry, here's the animation. So light from different points on the satellite interfere, creating a complex Fourier pattern. You can kind of see the shape there. And the spatial dimension becomes spatial frequency. In conventional imaging, say you wanted to image this geosatellite, here we have a 200-meter diameter telescope, so unrealistically large, but for simulation, this is what you would get. So a 200-meter diameter telescope would give us a high-resolution image of the satellite, and this kind of picture simulates what you'd get out of a perfect 200-meter telescope from the ground. And for reference, this is the Statue of Liberty. So from the ground, the base to the torch, it's 93 meters high, so about half. Yeah. Okay. If we were to use a 30-meter telescope, you can see that we can start seeing the higher frequency content is lost. And you can kind of tell that there's something there, but you don't really have much telling you what's going on there. If you keep moving down, 6.5 meter telescope, it gets worse. And then here's your 1 or 2 meter telescope. It doesn't really look like a whole lot. However, if we take two small telescopes and interfere them, and collect the light from these two telescopes and interfere them together, you get this one little slice of the Fourier plane. It's a little filled in. Ideally, you'd want the whole Fourier plane sampled to recreate a good image. So if you could move your telescopes around at different geometries and different spacings and orientations, so we can show our little dot simulating telescopes, we can see our Fourier plane being filled in. You would actually map out or recover most of your spatial frequency information that you would need to get the resolution that you would want. So you collect all that data and assume you did it all correct. You can do the Fourier transform and you should be able to recover the image in post-processing. So the predicted half-meter resolution from SPOT, the facility in Santa Cruz I mentioned, is comparable to a 40-meter conventional telescope. And so this kind of just gives you an idea of kind of the predicted simulated result of half-meter resolution image from SPOT. So sparse apertures can effectively give you this better resolution that we're after to image geo, but it's pretty complex. To get the resolution scaling with the distance between the telescopes, you lose some of the light gathering due to the Fourier plane's not a complete solid, and it's hard for geo objects compared to doing stellar interferometry on stars or something that's an astronomical source, because geo satellites are dim. We're looking at the reflected light coming off of the satellite, not it emitting light. And they're kind of complex. So they're complex asymmetrical surfaces, so you need a lot of higher spatial frequency information. Oops, sorry. Sorry. And that's actually one of the harder parts, is because their geosatellites are stationary. That's a bigger problem. In stellar interferometry, you can rely on the rotation of the Earth to fill in some of the spatial frequencies on the UV plane. And since geosats aren't moving anywhere, anytime you want to get a different slice from the UV plane, you have to physically move your telescopes, or you have to build a whole bunch of telescopes spaced out at different distances. And this is kind of the same idea that they used for getting that image of the first black hole. Instead of using they were using radio frequencies instead of visible, and they had the Earth spinning. So interferometric imaging is a concept built on the Van Sitter-Zernike theorem to measure the object's 2D Fourier transform. Your interferometer is really measuring the complex visibility, and to get your image back, you just have to take the data and do the math. There are a couple other ways to do this. What we showed is kind of this homodyne approach, where you take the light and use a delay line to interfere them. But you could do this in intensity space, but it has lower signal to noise ratio. The really interesting one would be heterodyne detection, because you wouldn't necessarily need to physically interfere the light that you collect, but you could use a local oscillator or some other source of the standard, interfere them with the same standard, and then and use that rather than physically. But you get a whole bunch of different complications with trying to do that. So currently the way we approach it is in the direct detect homodyne way. So there's definitely a lot of work to go on that. As I mentioned before, because the objects are stationary, you need a lot of baselines to be measured. Our approach for SPOT at least is to use a few telescopes that are moved around. But the Navy has a facility called NPOI, where they've built a whole bunch of stationary telescopes that have a particular geometry to fill out that 2D Fourier plane. Some of the technical challenges that we face with spot and interferometric imaging is affordable adaptive optics. We've worked with Michael Hart on some of the adaptive optics. Because light is coming through the atmosphere, if we want to do anything remotely well, we'd need good wavefront correction. And the way the spot facility works is that we use optical fibers as our to get our light to the delay lines. So once the light is received at the telescope, we transport it back to the delay lines in the beam combiners and optical fibers. Since we're moving our telescopes, it's easier to keep them connected via fiber. But there's a lot of challenges using fibers with the dispersion in the fiber and the different frequencies, fiber jitter, fiber mode, matching losses. And so doing it well is hard. Yeah, there's doing it well, and then there's just doing it. So trying to do this really well is really difficult. You could probably do it everything better in free space, but as you move your telescopes, that becomes more complicated. So in the case with the Navy with their stationary telescopes, that's probably easier to do in free space because they don't ever have to move their telescopes and keep all their delay lines connected. Yeah. And one of the other big technology challenges is having a global optical path difference knowledge. So you don't really have that knowledge because the light hitting the two telescopes have different phase distortions due to the different parts of the atmosphere that they're looking at. So you don't really know the answer unless you're measuring the atmosphere, and we don't really know how to do that well yet. So unless you're doing that directly, it's hard to know where the global point, where the optical path is zero, so that when you want to interfere these white light fringes, you need to adjust the delay line just right for them to interfere. So it's a big unknown in these systems, and you don't know what the atmosphere has done to the optical path to adjust for that. So it's one of the big challenges of getting fringes between the different telescopes. You know the length of the delay, from the end of your delay all the way to the beginning of the telescope, but you don't know what's happened into the atmosphere between what you're trying to image to get to your telescope. So how much do you really need to delay one relative to the other? So wrapping up on spot, the goal here is to provide 100-meter aperture. The largest baseline is 100 meters to give you that resolution. In 2014, they were able to get the first interferometric fringes in the I-band, and there's still more work to be done with it. Upgrade the AO that Michael Hart's been working on and getting that working really well. And then being able to measure at different wavelengths. So, yeah. This is kind of what we really wanted to talk about is SPIDER. So this takes kind of the same concepts of stellar interferometric techniques, and instead of thinking about how big can we build an imaging system, it's more about how much better resolution. How much better resolution by going bigger and better. So SPIDER is the segmented planar interferometric Planar Imaging Detector for EO reconnaissance. It's a hard acronym to ever remember. And so this is kind of the opposite approach of the stellar interferometric imaging. So how can we take a conventional imager and make it smaller? That's what I was trying to say. Instead of making it bigger and better, we're trying to make it smaller, more compact, and get the same imaging. So we work at Lockheed Martin Space, and so for space systems, as I mentioned before, size and weight are the things we often care about. So how do we apply this system that already works and improve on it on that system of a typical telescope? And so that's what SPIDER is. So it's like SPOT, but for stellar interferometric ground-based systems. So instead of moving all the telescopes like I mentioned in SPOT, SPIDER would do the simultaneous sampling instead of having to move the telescopes. So we would fill in, sorry, there's the conventional telescope, and here's our concept picture for spider, and these little spokes are little lenslet planes, and those would be the effective telescopes. So you're not getting the resolution improvement, but instead you're making the whole hardware footprint much smaller. And so again, it's a pupil plane detection versus an image plane detection, but it has the potential for low mass and low volume, and potentially can be reconfigurable so you don't have to keep it in this circular shape. So we're trying to go, instead of going bigger and higher resolution, we're trying to build something that achieves the same resolution but with a smaller footprint. So this is kind of a closer look at the system. The blue lines are the little lenslets that I mentioned before, so this is kind of a breakout of the two different lenslets. And behind them we have this photonic integrated circuit, and so we're taking light in from the scene and coupling it into the photonic integrated circuit using these lenslets onto the PIC, which is small, much smaller than the length of a telescope. And we're doing all the interferometric combination on chip. The spectral splitting, the beam combination, and the phase shifting are all done in a small piece of photonics. So we have these little heaters and the interference here, and we have an array waveguide. So again, your effective resolution is limited by the maximum distance between the two lenslets. So one side to the other of the photonic integrated circuit. We're not doing anything right now of like crossing multiple chips together or anything like that, but one chip would give you the resolution. In theory, you could hook up as many of the lenslet pairs as you wanted to get your resolution, but because the PICs do this so well, thousands of little structures in this small area, it's a powerful way of creating an interferometric interferometer. So rather than doing it free space, it can all be done on a chip. So this is a huge advantage. Instead of moving our baselines, we can just sample all of the combination lenslets simultaneously. So here's kind of the component breakout. So we have this low loss waveguide. We have phase shifters, these little heaters, to step the interferometric fringe along to sweep out the phase. We have beam combiners to interfere the light, and then the arrayed waveguides for spectral splitting. A question that a lot of people care about is what's the field of view, and how does this work for an imaging system? What can we expect? And so the coupling efficiency of the PIC varies with the field angle, and the field of view is determined by the back propagation of the waveguide mode into object space. That tells you the field of view. Once you start getting fancy with these, you could extend the field of view by packing a whole bunch of waveguides behind the lenslet rather than just kind of one, but we haven't done that yet. So right now the lenslet focuses light down onto the could focus it onto multiple waveguides, not just one, but we're not there. So the spatial resolution, as I mentioned, is the maximum baseline. So it's the spatial resolution of the imager and is determined by and determines the cutoff frequency. The way that we have it gives us the image quality that we want. It turns out that we don't have to hook up every lenslet pair. You could get some redundancy if you want. So this is an image of the lenslets that would be here. And if we hooked up these two next to these two, that would be the same frequency because they're only one spacing apart. So there's a little bit of science behind it of figuring out which lenslets you really need to pair out to sample the full UV Fourier plane with the least amount of pairs. So this kind of shows what we figured out to get. So you definitely want the two ends to get the longest baseline, and then you kind of figure out which ones to connect to get the other UV planes. So we don't need all of them. So this is basically the Fourier sample density. The baselines, the different lenslet pairs that you choose in the spectral channels are chosen so that you can get the sampling that you want. Fewer spectral channels are needed for shorter baselines so that it fills in the UV plane. And the lenslets, we call them big, or the lenslets, most people call them big. We call them small, but they're 0.72 millimeters in diameter. And we're operating in this 1200 to 1550 range. This kind of another picture showing the system with the kind of a little bit better description of the PIC. And then this is kind of the complicated lithographic layout that we're actually using. And so we're currently using this 3rd gen low resolution PIC using silicon nitride. It was originally using silicone, but this gave us a 100x reduction in area. It was originally like the size of a floppy, if you kind of know what floppies are anymore. But we work very closely with the UC Davis to manufacture these chips, and it kind of just shows how small and complex they are. It's about the size of a penny. That's doing all of our combining and interfering all together. And so when they do these runs, they actually make 24 of these on a single 6-inch wafer, and so you could make 24 of these little photonic integrated circuits at one time. So this is kind of our imaging testbed to show a proof of concept. So when we first started this project, we could do that single shot of making that kind of spoked layout, but we don't always have enough money to do that. So we took just one of those single PICs in the lab and tested that first. So kind of like the spot facility where you moved the telescopes, we kind of did that with the PIC. So instead we put our scene that we were looking at on a rotating mount to simulate the different frequencies that we were interested in collecting. It was a much longer collection time to take an image and rotate the scene, take another image and rotate the scene than it would be to take a single shot, but we showed that this concept works. And so this is our lab. Itai probably knows it kind of well. This is the part that got taken apart, but this kind of shows our object, our scene projector, and going into our PIC, and how we rotated it. So this video wasn't working earlier. Let's see if it works again. I might have to exit out now. So this movie shows the intensity at the output waveguide as the fast stirring mirror tilts that acts as the optical path difference to scan through the fringes. So you can kind of see it flickering on and off really quickly as it steers, and this is the output. I'll put this back into full screen so you can see. So the plot shows the measured intensity versus frame, and shows that we actually get interference between the different lenslets. And so the longer base lens have higher frequency fringes, as you can imagine. So a computer simulation example of the experiment. So here's our bar target in our expected image simulation. So through the experimental results, our initial image is kind of blurred due to the fact that as we rotated our image, there's some wobble in our scene that caused some of the phase errors. But if we applied some linear phase corrections above, we could get something that looks pretty close to the expected image. For a second test, we went for something a little more realistic, and so we did an aerial image of train cars converted onto this chrome on glass mask as our scene. And we applied a circular mask to image with that fast steering mirror again in our test setup. So this is the expected image just based off of simulation, and our experimental results agreed pretty closely. So the current and future work, so we want to improve the PIC throughput. We currently have 12 dBs of loss. Our goal is to get it down to 5 to 10. And we want the exposure time to decrease. The first test we did didn't have wire bonding to the optical path difference control. That's something we're adding on the next generation. And then we want to do this full 21 PIC lenslet to do a single shot. So that's kind of our current effort. We've kind of done all the CADing and modeling of how we're going to house it and align it and get it mounted into the housing so they're all aligned. And that's what Itai spent all summer mounting as our intern of how do I bond these lenslets into these with these little PICs and get it mounted into the housing, and then start integrating it into this big 21 array. So this kind of shows the fiber bundle and all the outputs and the housing. And this is the lab that Itai did a whole bunch, though, trying to fill in all of the picks so that we can take the light source and do a single shot image of this. So that's what we're working on, trying to complete this year. On the grand scale, this is really to provide a low-cost imaging sensor. The spiral radial blade that Itai is working on is an intermediate step. We'd really like to integrate the lenslets onto the chip, because doing the lenslet to chip alignment isn't easy, as Itai would know very well, trying to align all those lenslets. So we want to get rid of that process, so that's kind of a next gen for this. And instead of having to put these all on separate printed chips, if we could and mechanically mount the chip, if we could design the chip to be in the third dimension, where instead of them coming in for the edge and come down, we could easily couple into the chip a lot better. Putting the detectors on chip is something that we'd want for a future development. But this kind of, in closing, is how our system would in theory look. We'd have some really flat telescope on the front and get a Google Earth-like equivalent image. So yeah, that's all I have. Any questions?